I'm Daniela Jones. I'm an assistant professor in the Biological and Agricultural Engineering Department at NC State. I also hold a joint appointment with Idaho National Lab, and at NC State, I'm the Data Science Academy Director of Agricultural Analytics. In this video, you will see a project that we did as part of a class that I teach, Advanced Analytics, which is part of the Agricultural Data Science Certificate here at NC State, and I hope you guys enjoy the project.
Good afternoon, my name is Scott Carpenter. I am an agronomist and a master's student at North Carolina State University. And for years we had been working on farms to try and develop a foundation for these farms to work within a soil component. As a soil scientist, it's always good to know a variety of things such as the amount of clay that's in the soil, the soil color, the depth of the water table. All these things are very important for us to understand from a crop function. Historically, we've used a variety of tools such as a hand auger that you would use to auger down into the soil. 2 to 3 feet typically, sometimes deeper. Sometimes you might even use a measuring wheel to try and help you locate a boundary or a point that's in a field. The past 10 years, new technology has come out to allow us to do site reconnaissance using drone technology. While all this information is good, it's difficult for us to go out and collect information at high resolutions. So when I heard about this new soil optics device, sensor that you can mount onto an ATV, you can drive it across the field. About every 6 feet, it will collect information regarding it's a passive sensor. It actually collects radiation, natural radiation coming from the soil. Soil optics can then convert that information over to what they call a count rate point, and that point will be a reference to the amount of clay, silt, and sand. So then what that allows us to do is have a very high resolution map, as opposed to possibly hand augering every couple acres. You're getting soil information every 6 feet. This would allow us to more accurately predict things such as fertility loss, where to apply fertilizers, possibly yield estimations on sweet potatoes. And a lot of times this is very important for us during the growing season so that we can make in-season management decisions and adjustments perhaps, depending on the weather and how the crop is faring in the field. That we are collecting with the count rate, with the soil optics machine. We've also tried to integrate that information with other data that we have collected from combines, tractors, and sprayers, along with other soil fertility data and climate data such as the NOAA weather stations. As we brought all that information in, we created a tabular data set that combined that information that you will see in the model that helps us produce possibly an outcome that allows us to determine whether or not the soil optics machine is a valid way to go. Is it a higher accuracy? Is the trade-off for accuracy a better way to look at the information, or do we need to continue on with what we're accustomed to using, such as a hand auger and a
Hi, my name is Mariela Carvajal. I'm a PhD student at the Biological and Agriculture Department.
So as we're interested in predicting yield and count rate, we added environmental data from remote sensing. We made a script in Google Earth Engine to extract data from different sources for each point. First, from the satellite Sentinel-2, from which we calculated vegetation indexes and water indexes, such as NDVI and NDWI. Then for the WorldClim database, we used 5 bioclimatic data or data sets that are available there, 4 related with temperature and 1 with the annual precipitation. And finally, we also use the ALOS pulsar that had information from the digital elevation, and also we derived from this the slope. So by adding this data, we are accounting for the spatial variability and their possible influence in the target variable.
My name is Shani McDowell. I am a first-year PhD student in the Department of Biological and Agricultural Engineering. So initially we started with 2 separate data sets, and the data sets were at different scales. So we had a data set that was count rate information for multiple zones, and there was multiple points within each of those zones. And then we had different fertility data and yield data that was by zone. So we needed to combine these 2 sets together. And so the code that I'm about to discuss combines those different outliers for the yield variables. And we set boundaries for corn yield, soybean yield, and wheat yield. Then I went on to create a table of variables, all the variables that needed to be averaged. So I grouped the original data set by the zone ID and summarized. So we just came up with the mean of the count rate, the different corn yield variables, soybean yield variables, and wheat yield variables, as well as the different bio variables and indices variables on ID, based on the zone ID. So it removes the duplicate rows. Then that way we have a data set that is the same dimension as our averaged data set, so to speak. And I joined both of those together. There's also another portion here because we wanted to further explore soil type. And that soil type, we created a new categorical variable that's based off of the count rate. So if the count rate is below a certain value, then it's a certain soil type. So we the different soil types that we were looking at were sand, sandy loam, coarse sandy loam, medium sandy loam, and fine sandy loam. Just to have that categorical variable for different analyses that we were choosing to do. And I joined all of this data together based on the zone ID, and that was our new condensed data set.
My name is Jay Campbell. I am a research specialist in the Biological and Agricultural Engineering Department at NC State, and I'm also a part-time student studying advanced ag data. Included in my analysis were many of the fertility data points, also soil type, and then some of the other weather and soil factors. Also things like cation exchange capacity, organic matter, pH, and slope, just to see if that had any effect. For my corn model comparison pipeline, I started with a template of an advanced timeline for interval targets. For the pipeline comparison, the forest model was my champion. Under the error plot, you can see for the test data that validation and test both we're getting closer to zero. I believe that my stop point occurred at around 71 trees, so it was still within the range of 100.
My target data was the wet wheat yield. I ran a few different pipelines just to see what they look like. This is my first time running within the model studio, so I wanted to kind of see the differences between just the varieties of the pipeline, or of the different types of models, advanced models, an intermediate, an auto tuning, a risk model, and a feature engineering one. Truth be told, this is an interesting little approach because I'm not familiar with them, and so it allowed me to look at them a little bit more in depth and get some practice using them. So my comparison, after we ran all the pipelines and then we compared the 5 models, my champion was the forest model within auto tuning. And you can see some of my variables and the squared error percentages as they kind of went through. Again, here is the predicted mean when you look at the train value versus the test value. And as it drops off, I think I'm getting down to around 90 or so before it gets down to 0. I'm sorry, the most important variable within the model actually is the relationship between calcium and magnesium in the soil. And followed by things like potassium and sodium. And then actually count rate was in there too, kind of the top 4. I think these are interesting to kind of look at, pay attention to from a crop standpoint, from a fertility level, to possibly help make better predictions on wheat yield.
My name is Mariela Carvajal. I am a PhD student at the Biological and Agriculture Department.
For the soybean yield prediction, we built a model comparison with auto-tuning. SAS chose 6 models and made an appropriate pre-process like scaling and feature selection for some of the models like neural network and stepwise regression. In the Insights tab, we can see the summary of these results. And one of the important information that we have here is the most important variables for this model. The most important variable in this case was the bio-12, which is the annual precipitation. Finally, this actual versus predicted graph can help us to understand how the model performed with the train, the validation, and the test data. And in here, for example, we can see most of the errors occur at the first percentiles. And using this information, we can go back to the data and see if there's an error or there is a way that we can improve and have more accurate data and maybe improve the model.
My name is Enrique Peña Martinez. I am a PhD student in the Electrical and Computer Engineering Department. In this case, we're using the Build Models section in the Analytics Lifecycle from the SAS Vaya, which has been remarkably good at the collaborative experience between my team members. In this case, we are exploring 2 different models for predicting count rate. In this case, we're doing a 3 hidden layer network and a 1 hidden layer network. Actually get a good comparison between the models. At the end, we want to get a champion model that better predicts yield or count rate in this case.
I hope you guys enjoyed the analysis, that data integration, and the explanation of how we're trying to tackle this problem, this real-life problem with real data. The students have taken the first stab at applying machine learning algorithms through SAS Vaya, and the class is not over yet, so we'll continue moving forward with a deeper understanding of our problem and hopefully make an impact on industry.